So hello everyone, Assalamu alaikum. Welcome to my YouTube channel. So today I'm here for another data structure and algorithm related video. So today we are going to talk about Dijkstra's algorithm, or you can call it shortest path first algorithm. Now, just to start, we will go briefly over what this algorithm is about and how this works, and then we will quickly look at an example, a solved example, how to solve a graph using Dijkstra's algorithm. So Dijkstra's algorithm is used in shortest path first search, which is used in routing protocols specifically, which is also termed as OSPF, or open shortest path first. Now, what is a routing? A routing is a protocol that specifies how routers communicate with each other, disseminating information that enables them to select routes between any two nodes on a computer. Now, what is the shortest path first algorithm? This algorithm is widely used in routing protocols. It is also called the single source shortest path problem, in which the shortest path forms a single source, or you can say vertex, to all other vertices it has to be found. In the next example, I will quickly, or you can say in the next slide, I will go through, you will see an example of working example of how this algorithm works or calculates the shortest path from one node to another node. So for a given source vertex or a node in the graph, the algorithm finds the path with the shortest path between the particular vertex, and every other vertex. So we have a starting point, and from that starting point it will find the shortest path from that particular starting point to all other nodes in the graph. In this case, a Java applet has been used to show the process step by step. Let's quickly review that. So as you can see, it is this algorithm is finding this you can see the working of this algorithm through this animated example. So once a node, the shortest path from starting node to all other nodes is found, its job is done. So it will be out of the calculations, and then we hop on to the next shortest distance node, and in that way we will find the shortest path to all other nearest nodes, and we will go on repeating this process until we have finished finding the shortest path through all the nodes, or we have finished traversing all the nodes. So this algorithm has been used in GPS navigation system, and for a given source or in the graph, or you can say vertex in the graph, the algorithm can be used to find the shortest path from a single starting vertex to a single destination vertex. Now, how that works is, let's take an example. If the vertex of the graph represents cities, for example, and the edges represent costs, or they represent driving distances between pairs of cities connected by direct road. And then Dijkstra's algorithm can be used to find the shortest route between one city, let's say as it is marked here A, to another city, as you can see marked here as B. So this is what Dijkstra's algorithm is used for. And what are the requirements for this algorithm? It works with directed and undirected graphs. It works with weighted and unweighted graphs, and it is a greedy algorithm that produces an optimal solution. But do remember that it doesn't work well, or it doesn't work with negative weighted graphs. It always works with positive weighted graphs, not negative ones. So without further ado, let's do an example, quick example or a walkthrough of this algorithm, how this works. Now, as you can see, there are this graph represents, this is a directed graph that represents path or route starting from starting point to the destination point to different destination points. So let's say if my starting node is G and I want to find the shortest distance starting from G to all of the different nodes that it is connected to by either directly or indirectly. So I can use Dijkstra's algorithm to calculate that shortest distance from starting from G to every other node. For that, I can do so. There are different methods, but what I used to do is initialize an array that has 3 different values for each node that you see here. So for each node you have this first column which represents the binary value, either it is visited or not, it has been visited or not. So this only stores the value of visited and unvisited nodes in Boolean form. Initially it will be false for all the values, for all the nodes. Then the next column represents the distance starting from the original node or originating node or starting node to that particular node. For example, distance from G to A will be represented here. Okay, whether it is direct or indirect, we will see shortly how it goes. And initially all these distances will be marked as infinite. This starting node has a value 0 instead of infinite, we will see shortly. And this last column represents the value the node that we have reached from towards this destination node. So for example, this is our destination node and we are going from starting from G and we are going to A, and how we are reaching to A will be represented by this node, this value. You will see shortly how this is filled up. Now all the parameters are set. Let's start the algorithm. As I stated, this is your starting point. So initially all the values will be infinite. In just this G, this starting node has a value, will have a 0 value, and it will not have any prior node setting here, so it will be left null. Because we have already visited this node, so it will be represented with T or true value. Okay, so you can mark it as true, means that we have already visited this node. Now what are the paths or what are the nodes that are connected directly to G, or what are the nodes that we can visit via G? There are 2 nodes, H and D. Both of them are unvisited. As you can see from this column, both of them are unvisited. So we will calculate the distances starting from G to D and starting from G to H. So from G to D the distance is 2, or the cost is 2. So the column here at D will be filled with 2. And because we are coming from G, so this column will be represented with G, or you can say that you can fill this column with G because we are coming to D through G. Initially this is the value. Similarly for H we have 3, distance 3. So this H column, the distance of H column will be filled with 3, and we are coming via G, so this will be filled with G. This is how it works. Okay, we will only update if this distance is greater than what we calculate the distance in the next iteration. We will see that shortly as well. So this was the first iteration, and this is the updated value for nodes. Now next, how do we know that which node should we visit next? That is quite simple. The distance of the node, the value of the distance of the node will be the judge of which node to visit next. For example, in this case this node is already visited, so we don't look at this node. These 2 nodes are unvisited and updated. So what we do is we look at these two values. The smaller value will be visited. So in this case 2 is less than 3, so this node D will be visited next. I hope you get this idea. So when we visit D, then this column of D will be filled, representing that D has been visited. Now where can we go from D? We can go to either F or E. These are the two values, two nodes that we can go to. So these are unvisited, so we will see what are the updated values. So from D up to D, starting from G up to D, we have a value 2, and from D to F we have 18. So 18 plus 2 is 20, so we will update F with 20. I hope you get this idea, because we are not only counting this cost, but we are counting this G cost as well, because we have a starting point, a source point. Starting from source point, we have to count the value of cost. So from G to F it costs 20, and we are going to F via D, so this will be updated with D. Similarly to E, it costs 2 plus 25, which is 27, and we are going via D. So these are the updated values of nodes. Now again we have to decide which node to visit next. The next in line is H, so we will visit H, and the column of this visited or K value of H will be updated with true T value or true value. From H we can go to either A or B. Let's calculate what it costs to get to A and what it costs to get to B. So up to H it costs 3, and from H to A it costs 4, so it becomes equal to 7. So we are going to A and it costs 7, and we are going via H, so we will update this value, this column, via H. You will get to see shortly why this column is very important. Now next one is B. So we have the value 3 already for H, and 9 from H to B. So 3 plus 9, 12. So this column will be updated with 12, and this value will be updated with H, because we are going to B via H. So these are the updated values for the next iteration. Next up is which value, which node we can choose from this E, F, A or B. So A is the smallest distance, so we will naturally select A. Now A will be visited next. From A, where can we go? We can go either F or B. Let's see. F and B are already, they are not visited, but their values, their distances are already calculated. So let's see if the new distances are better than the previous ones. How they are better, how they can be better? When the new distances are less than the previous distance, then we will replace those distances. Let's check if this is possible for F. So up to A it costs 7 via H, and from going from A to F it costs 10. So it costs a total of 10 plus 7, which is 17, and F has a value of 20. So we will update this value, because this value is greater than the value that we have just calculated. So we will update only in the case if the new value is less than the previous value. So previous value is greater, so we will replace this value with 17. And now if we are replacing this value, then we will definitely replace this value as well. We are not going via D now, we are going via A. I hope you get this idea. Now from A to F we have calculated. Now we will calculate from A to B. Up to A we have cost of 7, and going from A to B it costs 15. which is greater than the previous value, so we will not update. So this is already the best value that we are getting, so we will not update this column. So these are the updated values after visiting the node A. Now, time to decide which node to visit next. This is the minimum value in the unvisited nodes section, so we will visit B next. So when we visit B, we have two paths, either go to C or E. So going from B to C, let's see, C is not updated by any node as any node, so we can update it without thinking twice. So going up to B costs 12, and going from B to C costs 4, so that makes a total of 16. So it will be updated with the value 16, and because we are going to C via B, so it will be updated with B. Now going from B to E, E already has a cost of 27. Let's see, the new cost is either less than or greater than this value. Total cost of going to B starting from G is 12, and the cost of going from B to E is 10, so that makes a total of 10 plus 12, which is 22, which is definitely less than the old value. So we can replace this one with this value 22, the new value, and because we are not going from D anymore, we are going to E from B, so we will update this value. Okay, so these are the updated values for the time when we visit node B. Now time to decide which node to visit next. Next we will visit node C. So when we visit C, we can only go to D. Let's see if D can be updated. Well, looking at this value, I don't think it needs update, but as a formality, you can see 16 plus 3, which is obviously greater than this value, so it doesn't need to be updated. So these are already updated values. Next, we have only two nodes remaining. So going from so we have these two values. So next we will visit F, node F. So starting from F, we can go to B, C, and E. Let's see if there is any update needed. F to B, up to F costs 17, and F to B costs obviously greater than 12, so it doesn't need to be updated. Now F to C, let's see. Up to F it costs 17, and it is already greater than 16, so it doesn't need to be updated as well. What about E? Let's see. Up to F it costs 17, and F to E costs addition of 2, so it means it costs total of 19 to go to E, which is less than 22, so we will update this value. And because we are not going from B anymore, so we will replace this value as well. We are going from F. So these are the updated values of after we have visited F, and the last one to visit is E. When we visit E, then we cannot go to G because this is the starting point, so we will not update G. Then we can look at D. D is already a very much small value, so we do not need to update this value as well. And that's it. Now all the nodes are visited and all the distances have been calculated. As you can see, the red are the routes that we have formed. If we want to go from, for example, G to B, then this is the route. Similarly, if you want to go from G to A, then this is the route. Or if you want to calculate from find out the value or the route from this, if I want to go from G to C, you can see starting from G to C, we can take the route G to H to A, to B to C. So this is the route that it can take. It cannot take any other route. Okay, so this is how you calculate the shortest distances to all the nodes via Dijkstra's algorithm. I hope everything is clear now. If you have any questions, leave a comment, and until my next video, if you need more videos on more algorithms, then please comment below so I can make more videos. Until next time, take care.